Hello everyone. Today I'm going to talk about the paper named Deep Image Prayer from the conference of CVPR 2018. Let's go on with the presentation. First of all, we should talk about what makes image restoration difficult. As I said in my previous presentation about the MRPF and NET method, which uses a learning algorithm separately. Uh, as I said in that presentation, noise, blur effects, missing pixels have some bad effects in image restoration, and uh, these effects cause some information loss when reconstructing the image. And there are some papers uh, in, about these methods, and everyone is trying to get some ideas about the algorithms. In my first presentation, I talk about the algorithm which uses a separate CNN and low pass filter algorithm. And in this presentation, in this paper, uh, deep learning prayer, there is a very different idea, and that may be crucial. I will talk about this. First of all, let's talk about what is the aim of deep learning prayer. The main aim of deep learning prayer is without using a data set, without using a training, what can we achieve in learning algorithm in this type of reconstructions. Nowadays, in most of the algorithms, a data set and a training process is used in the especially in high frequency CNN processes, as I told in the previous paper. But in this paper, uh, they are trying to prove that without using any data set, we can still get good reconstructions without using some data set, and we can reduce the cost because there is no data set training process. And also, they say that some of these dataset usage may affect the results bad. Let's talk about them. Let's talk about them. Just a second, please. As I said in the previous slide, the key idea of deep image prayer is not using a training data, and because of not using a training data, you initialize the CNN randomly, not with specific parameters. That's crucial. Also, because of there is no training, the cost is reduced, and the randomly initialized CNN will have some effects, and we will talk about them. Let's talk about the deep image pre-formulation. That's crucial. First of all, how is image restoration traditionally formulated? Mathematically, deep image pre represents the clean image as an output of neural network. Instead of directly optimizing image pixels, the image is parameterized as it's seen x is equals to f over theta z, where f over theta z is convolution network and z is a fixed random noise input. That's crucial. The main idea here is trying to investigate, predict the difference between the observed output and the network output. I can say that the difference between the degraded observation and the network output. That's crucial. Actually, we can say that in signal processing, the error. We can say that. The optimization is performed over the network parameters, not over the image itself. That's crucial. The objective is to minimize the difference between the network output and the graded observation, as I said. This formulation implicitly constrains the solution space because only images that can be generated by the CNN architecture are considered. There is uh, in this in this paper they didn't use any other filters. They used CNN algorithm, but without using any data set. Let's talk about the different formulation of deep image prior. During optimization, the network is initialized with random parameters and gradually fits the degraded image. As important observation that CNN learns natural image structures much faster than random noise. This means that at iterations the output image already looks clean and structured, while noise fitting happens later. Therefore, early stopping plays a key role and acts as an implicit regulation mechanism. Let's talk about why does this method work? Because okay, we got the idea, we got the, we have learned the aim of them and what they are trying to do, but why does it work? It does work because of the CNN's inductive bias, because of the noises learned later. The process is done better because the data the data loss, the information loss is not uh, not as much as in the normal algorithms, normal CNN algorithms with trained with data sets. Also, uh, during optimization, the network learns meaning image structures first, while noise is learned much later. By stopping the optimization early, high quality restoration results can be obtained without fitting noise. CNN have a strong inductive bias towards natural image structures, and these are the main reasons of the working principle in deep image prior. And we talk about all these, but also we need some evidences, and the paper's authors have gave us some experimental results, and we are going to look at these. Let's go. First, I will show with my cursor. In the left, we can see the original image. Let's talk about the first one first. We can see the original image, and that's the corrupted one with a little noise. That may be a Gaussian noise or another, but this is corrupted with a noise manually in order to test the product. And these are the algorithms, and deep image prior is the algorithm that we are looking for. Let's see the results. As we can see, the math of the woman is much sharper in deep image prior, and in addition, there is no dataset used in deep image prior. Actually, the difference here is the dataset usage, because in my previous paper presentation, there were an algorithm difference, but there is not an algorithm difference. The main difference here is, of course, there is an algorithm difference, but the main idea of deep image prior is not using a dataset, not training. And Shepherd network uses a dataset, and the result is here. Let's go on with the second example. We see the original image here, and as we can see, this is the corrupted one. And as I said in my previous presentations, the the uh, more PSNR value, the more VSNR value is, uh, the better the reconstruction is. And we can see that the PSNR value of the photo G is much smaller than the deep image prior. And we can see with our eyes actually. It's not just mathematically. We can see with our eyes. When we look at the spaces, the colored spaces, we can see the differences. Also, we can look at the other example. There's a butterfly wing, and when we check, this is BQBX not trained algorithm. This is ours not trained algorithm. Also, I should talk about the difference here. The main we said that the main difference is no training, but also they show that their the algorithm they developed is much better when using the same training method. Of course, the non-training method, because the BQBX non-training methods example, the result is here, and ours, the deep prior is here, and ours is much better. And these are the trained ones. We can see the some blur effects with I'm showing with my cursor. We can see the blur effects here, and when we look at look at generally with the photo, okay, the construction is good, reconstruction is good, but when we look at the details, there are too many not good things here. But of course there are some in our not trained algorithm, but we should say that the main idea in this paper is in this paper uh, they they do not say that their non-training method is much better than the other methods. They just say that we can still achieve the same quality without training, because nothing everything is not just getting a better result. In every reconstruction we use some uh, money, and every of them has a cost, and that's why they say that achieving the same quality of reconstruction is possible without using a training data. That's crucial here, because they do not say that our algorithm gives us much better results. That's crucial. In conclusion, deep image prior demonstrates that a convolutional neural network architecture itself can serve as a powerful image prior. The method does not require any training data and performs the image restoration through per image optimization. Despite its simplicity, deep image prior produces visually convincing results on various restoration tasks. This work challenges that the assumption the large data sets are always necessary for effective image restoration, as I said. Deep image prior provides a new perspective by bridging classical image priors and deep learning approaches. Thanks for watching my presentation. That's the end of my presentation. Have a nice day.